Good day everyone. So today we're gonna solve the problem 6.5 of deflection of beams. But before we proceed, let's define first what is deflection. So deflection is the vertical displacement or bending of a structural member from its original position when subjected to loads. So para mas maintindihan natin kung ano nga ba yung sinasabi ng deflection, let's try to illustrate. For example, meron tayong ruler. Yung ruler daw natin is may dalawang support. So kapag naglagay tayo ng load sa gitna, yung ruler natin is mabebend downward. So yung bending na ito, yan po yung tinatawag natin na deflection. So deflection is represented by V quantity of X. So let's go back to our problem. So according to problem 6.5, solve problem 6.4 if the coupled moment acting at the left support is removed. So according to problem 6.4, the simply supported beam carries two end couples, each of magnitude moment but opposite directed. So find the location and magnitude of the maximum deflection. So isulat muna natin yung mga required. So ang mga required natin is yung location at yung ating maximum deflection. Sabi sa problem kanina, ang beam daw natin is what we call simply supported beam. So simply supported beam is characterized by having a pin on one side and a roller on the other side. So simply supported beam also, it doesn't allow any vertical displacement. So the deflection for our beam is 0. So let's now proceed to our free body diagram. So for our free body diagram, since yung A natin is roller, meron itong tinatawag na normal force. So let's assume that the force in point A is acting upwards. Sa point B naman, since yung point B natin is a pin, meron itong dalawang force. Meron itong horizontal at saka vertical force. So, pero sa case natin is ina-neglect na natin itong horizontal force since there is no external horizontal load acting on the beam. So, ang matitira na lang is itong ating vertical force. So, let's assume that the force here is downward. Since sabi sa problem kanina, hindi daw natin kailangan or pinapatanggal na itong moment sa left, so hindi na rin natin siya isasama sa ating free body diagram. So sabi kanina, ito daw figure natin is a simply supported beam. So ang simply supported beam is analyzed in a static equilibrium. So kung inalis na natin itong moment dito, hindi na siya in equilibrium. So paano siya mababalik sa pagiging equilibrium? So dito na po papasok yung ating dalawang vertical forces. So yung vertical forces natin is kailangan mag-resist or mag-oppose dito sa ating applied counterclockwise moment. Ibig sabihin, yung direction po ng ating vertical forces is kailangan na clockwise. So i-check natin yung ating FBD kung tama yung ating assumption. So, kapag inibo natin itong ating RA pataas, mag-move siya clockwise. Same as dito sa ating RB, pag inibo natin siya pababa, mag-move to clockwise. So, tama yung ating assumption. So, these two forces produced moment equals force times the distance. So, for the beam to remain in equilibrium, the resisting moment must be equal to the applied moment. So, force times our length is equals to the applied moment. So, solving for the F, we have force equals applied moment divided by our distance. So, i-equate natin itong ating dalawang forces sa ating nakuhang sagot. So, after natin magawa yung ating FBD, is magpo-proceed naman tayo sa paggawa ng ating or sa pag-draw ng ating internal forces. So while the free body diagram shows all the external forces and reactions acting on the beam, it does not show how the beam behaves internally. So to determine what is happening inside the beam, we will now analyze its internal forces. So paano po natin gagawin or paano po natin ipapakita yung ating internal forces? So ang gagawin po natin is hahatiin natin yung ating beam into 2. At ang kukunin ko po dito is itong left side. So let's try to read. Copy lang natin yung forces kanina. So this will become x, yung distance natin ay magiging x. So sa internal forces, meron tayong tinatawag na normal force, shear force, at saka yung ating moment. So while internal normal and shear forces exist, the normal force is 0 due to lack of horizontal loading. And the shear force is not required for our deflection calculation. So we will just focus on the bending moment because it is the governing factor in the Euler-Bernoulli equation for the beam curvature. So let's proceed to the summation of moments. So magmo-moment tayo sa x at the x. So this will be equals to 0. Yung RA natin is magmo-move or nagmo-move siya clockwise multiplied by our distance x. Yung moment naman natin from the internal force is moving counterclockwise. So, natin siya ilalagay. And now, we have our equation for the bending moment function. So, after determining this, the next step is to relate this to the actual deformation of the beam. So, this is done using the Euler-Bernoulli's beam equation. So, ano po yung Euler beam equation? So, ito po yun. Where the EI is equal to the flexural or flexural rigidity. So, kung mapapansin natin, yung ating equation is equal dito. So, what we'll do is we'll just substitute. So, we will get moment divided by the total length times the position. Now, this is our governing equation. And now, we will proceed to the double integration method. So, ano po yung sinasabing double integration method? So, double integration will help us to find the slope and the deflection equation. So, the first integration, it will give us the slope function. And for the second integration, it will give us the deflection function. So, let's start with the first integration. So, i-copy lang natin yung ating governing equation. So, using our basic knowledge of integral calculus, since this is a constant, we will just copy it. And the x will become x squared over 2 using the integration power rule. Don't forget our arbitrary constant c. After combining, we will get moment divided by 2 times the length, x squared plus c sub 1. So, this is now our equation for the slope. The next one is the second integration. So, for the second integration, ang gagamitin natin equation is yung function na nakuha natin sa ating first integration. So, equal to the integral of moment divided by 2 times the total length, x squared plus c sub 1 dx. So just like what we do earlier, let's copy the constant. The x squared will become x cubed over 3 plus, since c is a constant also, we will multiply x and our arbitrary constant c sub 2. So after combining this, we will get the LV is equals to the moment divided by 6 times the total length, x cubed plus c sub 1 x plus c sub 2. So this is now our equation for the deflection. So kung papansin natin, after natin mag-integrate ng dalawang beses or after ng process natin ng double integration, meron tayong dalawang unknown constant. So alin po dyan yung unknown natin? Ito pong c sub 1 at saka po itong c sub 2. So ano pong gagawin natin para mahanap po yung value ng mga yon? So kailangan po natin ng tinatawag na boundary conditions. Ibig sabihin po, kailangan po natin mag-set ng coordinates at reference point. So, let's try to go back to the given figure. So, ipagpalagay po natin na yung point A natin is our starting point. So, our A will become x equals 0. Yung B naman natin is our end point. So, this will become x equals L. So, bakit po siya L? Kasi po, from the starting point to end point, ang distance po niyan is equals to L. So, isulat po lang po natin yung ating mga nakuhang coordinates. X equals 0 at x equals L. And nabanggit ko rin po kanina na yung ating deflection is equals to 0. So, isasubstitute lamang po itong mga nakuha nating coordinates dito sa ating deflection. So, after po nating makuha yung mga boundary conditions, ano pong gagawin natin? So, ang mangyayari dito is isa-substitute natin ito sa isang equation. So, ano pong equation yung gagamitin natin? So, ang equation po na gagamitin natin is yung equation from the second integration. So, bakit po kaya? Kasi po, yung second integration ay tungkol sa deflection. At yung boundary conditions natin is tungkol din sa deflection. Kaya po, ang kailangan natin na equation ay yung may deflection din, which is yung result ng ating second integration. So, simulan muna natin sa x equals 0 na coordinate. So, i-copy natin muna yung ating equation. So, sa lahat ng x natin is papalitan natin siya ng 0. So, let's substitute. So, simplifying, this will become 0 plus 0 plus our c sub 2. So, the value of our c sub 2 is equals to 0. So, mag-proceed naman po tayo sa ating x equals L na coordinate. So, i-copy po ulit natin yung ating equation from the second integration. So, sa lahat ng x naman natin, ang isa-substitute naman natin ay L. So, plus c sub 1 our L. Since nakuha na natin yung value ng ating c sub 2 is 0, hindi na natin siya isasama. So, simplify, we will get c sub 1 equals negative moment times the length divided by 6. So, ito na po yung ating mga value for the unknown constant. So, after po natin makuha yung mga value for the unknown constant, ano pong gagawin natin? So, ang gagawin natin is, isa-substitute natin ito, pabalik dito sa ating equation from the first at second integration. So, simulan muna po natin sa slope. Sulat natin. Final equation for the slope. Ano nga pong equation natin sa slope kanina? Diba ito? So, kakopy lang natin ulit. Since nakuha na natin yung value ng ating c sub 1, is isa-substitute natin ito dito. So, we will get minus our c sub 1 moment times the length over 6. So, since maximum deflection occurs where slope is 0, i-equate natin itong ating whole equation sa 0. So, this will becomes So, now, we will solve this equation to find the value of x. So, the x tells us the exact location along the beam where the maximum deflection happened. So, ang una natin gagawin is, i-divide muna natin ito sa ating moment. So, ang matitira na lang is, hindi makakancel ito, matitira na lang is x squared over 2 times the length equals, and then, x squared equals 2l divided by 6. Since itong ating x is naka-raise to 2, ay kailangan nating i-square ang ating whole equation. So, x is equals to L divided by square root of 3. And now, nakuha na natin yung isang required, which is the location. So, itong x na ito yung position kung saan nangyayari yung maximum deflection natin. So, x, this is the location. Now, we will proceed to the final equation for the maximum deflection. For the maximum deflection. So, copy lang ulit natin yung ating equation from the second integration. So, plus c sub 1x plus c sub 2. So, ano nga po ulit value ng ating c sub 1 kanina? Diba ito yon? So, isa-substitute natin siya dito. So, minus 6x. Since ang value ng ating c sub 2 ay 0, hindi na rin natin siya isasama sa ating equation. So, di ba nakuha na natin kanina yung ating location? So, ang gagawin natin is isa-substitute natin ito dito sa ating mga x. But before we do that, let's equate this equation first to v, since deflection is represented by v, quantity of x. So, to do that, v equals, i-divide natin yung ating whole equation by ei. So, ei quantity of cube minus the moment times the distance over 6 times dx. So, we will now substitute our location. So, simplify. This will become L cubed over 3 square root of 3 minus, if we multiply this 2, we will get moment times the length squared over 6 square root of 3. So, simplify again. This will become, this one will be cancelled. So, L cube will be L squared. So, if we multiply, we will get 18 square root of 3 minus moment times length squared 6 square root of 3. Kung mapapansin natin, magkaiba yung ating denominator kaya hindi pa natin siya madadirect subtraction. So, what we'll do is we'll multiply this to 3 over 3. So, 6 times 3 over 3. And we will get 3 divided by 18 square root of 3. So, we'll just rewrite. Since parehas na sila ng denominator, pwede na natin silang ipag-subtract. So, after natin ma-subtract, we will get negative moment times the length squared over 9 square root of 3 times the flexural rigidity. So, kung mapapansin natin, yung ating maximum deflection is negative, meaning our beam is deflecting downward. So, in beam sign convention, kapag ang sagot natin is positive, meaning yung deflection is upward. So, kapag negative naman, the beam is deflecting downward. So, our answer will be moment times the length squared divided by 9 square root of 3 multiplied by flexural rigidity deflecting downwards. So, this is now our answer for the magnitude of the maximum deflection. So, I hope you learned something today and thank you for listening.